Morning class, soil compactions. So we're going to continue our soil compactions. Okay, great. I already showed you have standard compaction test and modified test, modified compaction test. When you do this compaction test, you're going to get a typical compaction curve. This is a typical compaction test results. So within this curve, you have the dry unit weight over this moisture content. In this compaction test, it is actually conducted in several moisture content. The main idea is to obtain the maximum dry density at optimum moisture content. What does it mean by maximum dry density? Maximum dry density, this is dry unit weight or maximum dry unit weight. So when you plot, each and every time when you plot this compaction test, you're definitely going to get this curve. This is what we call a compaction curve. This is a typical curve. It starts from a very low amount of dry unit weight, as you can see in here. Then as your moisture content increase, the unit weight is also increase. Okay, so as your moisture content increase, the unit weight also increase. The maximum dry density is actually at this point, and maximum dry density is actually at the peak of the curve. So this is typical curve. So that's why it's called curve. You're going to see lots of curve. The top part we call maximum dry weight or maximum dry density. This is the optimum moisture content. And as you can see that in this is what we call zero air void. Okay, so the zero air void line, okay, so this line, the line that you can see in here, this line, zero air void line, although compaction will increase dry unit weight, there is actual limiting in dry unit weight for any moisture content, and this occurs when the void are full of water. This line is known as the zero air void line. Okay, as the compactions, as the soil compacts and the void is actually reduced, and this causes the dry unit weight or the dry density to increase. As you can see in here, this is what we call a zero air void line. So within that zero air void line, you actually can go much higher or much lower. With that indication, meaning that if I put it somewhere say at this point, so you're going to see that this is going to give you this dry unit weight, this be able to give you this dry unit weight, and this have this one, and this have this value of optimal moisture content. Okay, but it won't goes beyond this boundary. So the compaction curve line, okay, as the moisture content increase, so does the dry unit weight. Increase the water content for a saturated soil resulting in reduction in dry unit weight. Water content effect is this water content effect. As water added to a soil at low moisture content, it becomes easier for particles to move pass one another during the application of compacting force. As the soil compacts and the void are reduced, and this causes the dry unit weight or dry density to increase. Okay, initially, as the moisture content increase, so does the dry states. Okay, as the states will later approach the no air void line, the maximum the moisture content at this maximum is called the optimum moisture content. As you can see that when you increase the moisture content, you'll be able to increase the dry density as well, right? So the increase cannot occur indefinitely because of the soil straight approach to the zero air void line, which gives the maximum dry unit weight for a given moisture content. Thus, as the states approaching the no air void line, okay, further increase of water content must result in reduction in dry unit weight. So as you can see in here, so the increase of water content, when you pass this point, you're going to reduce dry unit weight. So you can see in here, too little water, lower the compacted, the density of soil, and then you increase water, then you have the maximum dry density at optimum water content. Then when you have this one, then you have too much water, okay, and it's actually lower the compacted density of the soil. Effect of compactive efforts. So as you can see in here, when you increase the compactive efforts, it is enables to the greater unit weight to be achieved. The moment that you increase this compactive energy, the curve is actually be able to shift from one point to another with the same amount of water. If you increase the amount of energy, actually be able to increase the dry density or be able to increase the ability for that soil particles to move. The moment you give the energy, soil particle will start to agitate, it will start to be able to move and start to rearrange. Okay, the more energy that you give, and you're going to have much more energy, much better for that soil for it to move from one point to another. But it should be noted that for moisture content greater than optimum, the use of heavier compact machinery will have only increasing dry unit weights. Increasing compactive efforts enable greater dry unit weights to be achieved. So this is when you increase, and you increase. This is just consider the same soil. This is 5 blow per layer, 25 blow per layers, 30 blow per layer, 50 blow per layers. Okay, basically each and every that blows give transfer, right? So if you increase the numbers of blow, basically you are increase the amount of energy as well. You are actually increase the dry unit weight. Moving on to the third part, okay, in the compactions, this is effect of soil type. So as you can see that this is sand, clay, polygraded sand, low plastic clay, this is silt, this is clay. So this is typical value of maximum dry density. And this is typical value of optimum moisture content. You can see that most of clay or silt, okay, it is usually have a very low amount of maximum dry density, but a very high amount of optimum moisture content. And as you can see in here, this is sand. Most of when you have at the higher peak is actually sand compared to clay. So this is 7 heavy clay. Sometimes when you compact clay, you will notice that it doesn't have that peak. it won't significantly seems like having the normal compaction curve. So, which is why each and every time when you deal with clay, we usually go towards an ground improvement techniques or soil stabilization techniques in order to increase its shear strength, its compressibility, stability before you actually start doing any construction works. The ground improvement and soil stabilization is taught in fourth year if you are taking an elective course. Okay, compaction quantified. Compaction quantifies what most important in compaction is actually your ability to understand the purpose of compactions as well as when you want to compact and when you should have a look on a different soil stabilization or ground improvement methods, okay, when you start working. And this is actually more important as well as how you actually be able to control the quality of the compaction at sites, okay? Because ensuring the quality is very, very important. Okay, come back to this one, compaction quantified. It is quantified in terms of dry density and compute in terms of bulk density. Why bulk density? Because this is the amount of soil that you can actually get at site. And moisture content, okay, moisture content and dry density can be measured directly, but we can measure the bulk, okay, density as well as the moisture content. So hence dry density, it is expressed as this one, gamma dry, it's gamma bulk over 1 plus the moisture content. Okay, so this is one examples. This one is actually taken from Munibudu, okay, in page 76. So you can actually check in Munibudu compaction calculations. So this is one example. So you have a water content. As you can see that water content is increasing, okay. Then you have bulk unit weight. You can actually see the patterns. You can actually see the patterns in here. It is actually increase, then after that is reduce. Okay. So although that the pattern is visible, but you need to understand that you need to plot this one. So once you plot the curve, then you can actually get the actual maximum dry density from that. This one you can try, okay? Plot the compaction curve to find maximum dry density and optimum moisture content. So you can actually calculate the dry density based on this one. Then once you already get in the table of the dry density, after that, you plot the graph, okay? You plot the graph, dry density against water content, so you can get that curve, right? That compaction curve, the increase then reduce. Then from there, you can actually get the maximum dry density as well as optimum moisture content. Okay, second, determine dry unit weight and water content at 95% of standard compactions. Okay, so at 95% of standard compaction means that the value that you get at the peak of your curve, you multiply by 0.95. So once you multiply by 0.95, then you will get the dry unit weights. Okay, and after that, we'll be able to get the water content at 95%. Okay, that is water content at 95%. Okay, you can try plot zero curve and void. Okay, so this is actually 100% saturation, 95% saturation, or 90% saturations. And you can as well as determine degree of saturation at maximum dry density. So this is the solutions. You can actually plot, as I mentioned before. You can actually calculate the dry unit weight. Once you obtain the maximum dry density or maximum dry unit weight and optimum water content, then after that, you can actually plot the zero air void ratio. Zero air void means this one saturation is 100. Okay, so this one means 95%, and this is air saturation at 90%. And if you want to know the degree of saturation at maximum dry density, so you can actually rearrange the formula and you can actually change to make it S at the front and can put all the values in here. Okay, so this is specific gravity, optimum moisture content. Okay, so on next class, we're going to continue on field explications. Okay, so thank you very much, guys, and see you guys on our next class, okay, on Friday. Okay, thank you. Have a great day today, okay?